So we're just going to start by going through the notes again quickly, and I'll just highlight the relevant stuff. So I hope by now a force being a push or a pull is not too odd for you, and that it's measured in newtons, and that it's a vector. So all of that, yes, it's relevant, but hopefully it's also kind of a given. The first law is important to remember. It shows up more as far as solving problems in that if something is moving at a constant velocity, that tells you that the net force on it is zero, and vice versa. If the net force on something is zero, it is moving at a constant velocity. So if you're given a problem that says something's moving at constant velocity, that immediately tells you the net force on it is zero. And so if it asks you to solve for a particular force, that just comes out of the balancing of all the forces that has to happen. You'll be given enough information about all the other forces to kind of say, what does that one you're looking for have to be to make the net force zero? And you do that by breaking into components and summing the forces. So pretty much this process that we'll get to with the second law. As far as reference frames, this was setting the stage for when we can and can't use Newton's laws. We can only use them in inertial reference frames. The Earth is roughly inertial because inertial pretty much means just not accelerating. The Earth is accelerating, but it's a pretty gradual acceleration for most things we're interested in, so we can ignore it. That's really all that's relevant here. So as far as the exam goes, you don't have to think through these sorts of things. We just say Newton's laws work for us, and that's how we justified it. Instead of being told that something's moving at constant velocity or has a net force of zero acting on it, you could be told it is in equilibrium. That means the same thing. All the forces acting on it are balanced. So you won't be asked to distinguish between static and dynamic equilibrium or something not being in equilibrium. Again, it mainly just shows up in solving problems. Mass, again, kind of, we have some intuitive sense of mass. It's not tested per se, other than that it measures inertia, maybe a relevant thing to remember. So because things have mass, they have this resistance to changes in their motion. And so they want to keep moving the way they were moving prior to some force acting. And that affects how they move as a result. The larger the mass, the less the motion changes. And by that, I mean the smaller the acceleration. So it's more a conceptual thing. This definition is a little bit obtuse. That's not going to be on there. But knowing that mass is measured in kilograms may be helpful in that if you're given something in kilograms, that's a mass, not a weight. Second law. We've been using it in this form. That's the condensed form, but the idea is that the larger the net force, the larger the acceleration of something, the larger the mass, the smaller the acceleration. So this was when the stylus went out, I just went back in and filled these in. But the unit is a Newton. You don't necessarily need to remember what a Newton is, but it is a kilogram meter per second squared because that's the way the units work out in this expression of the second law. We use it in problems in this form. We break stuff into components along different axes and then treat each of those axes independently. The only thing that sometimes connects what's happening along one axis or another is you've got something like friction, which depends on the normal force. So that you have to figure out the normal force along the vertical axis to figure out friction along the horizontal axis. Or you could have a system of objects and you're asked about their acceleration. So systems primarily for us are like it's called an Atwood machine. That's not really relevant, but like if I've got a certain weight for this one, it's like 30 newtons, so roughly 3 kilograms mass, and 50, and I let that go, what's the acceleration of the system going to be? And um, there could be ones like something is hanging off a table or it's on an incline. So there's a couple like that on the practice exam as well. But it's the idea of analyzing each of those separately. And so there's an example we did of that somewhere here coming up. Free body diagrams, absolutely 100% are on there. You have to be able to draw a free body diagram, not only for credit on problems, but also to be able to solve the problems. We just use them to do that. So certain problems will say a free body diagram is required to get full credit on the problem. So even if everything else is done right, if there's no free body diagram, that's a significant cut off the grade. These are just the rules for this. Should have filled in here collections of objects. You should have that, but collections of objects. So this kind of thing does not come up so much for us. Distinguishing between external and internal, that's mostly how we sort of develop some of our tools, is at certain points we have to think about that. So it may help to think of this for a system. Sometimes it can make things go faster, but I would still recommend just treating each object separately, like we see with a problem a little bit later with two blocks connected by a string. These are not bad problems to look at. There will be harder ones than this on the exam, but there are some that are fairly similar to probably primarily this last one on the right. There could be one that's just a couple horizontal forces. Well, there are, but you got lots of different types of forces acting. So you're not just given a magnitude. There'll be some extra work on finding the magnitude of certain forces. Gravitational force, the only things you need to know are that its magnitude is mass times gravitational acceleration, and it always acts straight down. If you're on a ramp, the weight does not still act towards the ramp, it acts straight down still. So if we've got something on an incline, the weight is still straight down. It is not that way. What is along that axis is the normal force. It does point that way. It does not point vertically up. Okay, so that's something to note about the normal force on inclines, because there is at least one problem about something on an incline. But the idea of the normal force is if something is on a table, sitting on it, sliding on it, on any sort of solid surface, there is a normal force being exerted on it by that surface. If there weren't, gravity would be the only downward force pulling on the object, and it would fall through the earth, fall through whatever supporting surface is there. So that normal force is there to balance other forces that are acting vertically so that something does not fall through tables and the ground and things like that. So that can mean in some cases that it's equal in magnitude to the weight of the object because that's what it has to balance. But there are cases where it's balancing more than just that, like you push down on the object. In that case, the normal force is not equal to the magnitude of the object's, the gravitational force. It's equal to whatever it has to be to balance things out, or if something's accelerating, it can actually be what's providing that acceleration. So that's the case of something in an elevator. There could be like one elevator type problem of you're given someone's mass and you want to know for a given acceleration what the normal force on them is. So it may word that as what reading would a scale say, or with what force does the floor of the elevator act on this person, things like that. But pretty much the whole solution for any of those types of problems is right there. It's just choosing your type of acceleration and plugging in some things. Hopefully it makes a little bit of sense intuitively though, because if you're going upward in an elevator, it's accelerating upwards, you'll feel like you're kind of being pressed or pulled into the floor. You feel heavier. A scale will, in fact, read a larger number because it's measuring that increased normal force that the ground exerts on you and so that you exert on the ground. And if you're slowing down, you're decelerating, you'll feel lighter. If you're moving at constant speed, you will not feel any difference in your weight. Tension. Tension is like normal force in that it's just there to kind of make the math work out as far as problem solving. It's just there to either ensure that something is balanced, like it's not moving, it's in equilibrium, or else moving at constant velocity. That could also be a net force being zero. Or it could be the thing causing acceleration. There's no like formal equation for it that always determines it. It's just determined by what the object it's pulling on is doing. So let's see. The assumptions for why we can treat this tension as acting uniformly on the whole rope are not tested on. But it is very important to realize that it is always acting to pull on the object. So you can't push with a rope and you can't push on a rope. So it's just pulling back on whatever is acting on it. And so you got to be careful with your directions. It's easy to get confused. Like one of these, you might be tempted to draw the other direction. But if you're interested in a free body diagram, or if you've got like two blocks, that Atwood's machine, the tension's going to act upward for both. And it's going to be equal for both. It's the same rope, it's the same tension. If you have two different ropes, it could be two different tensions, but if it's the same rope, it is a constant tension throughout that it's applying on other things. Third law. The third law is how we're, I guess, explaining why the forces are acting this way. So the reason the tension pulls upward in this first picture on the hand is because the hand's pulling downward. And Newton's third law says those forces should be equal and opposite. Same up here. If the block's tending to pull left on the rope, then the rope's pulling right on the block, or it could be that we know about the rope pulling right on the block. That tells us the block pulls left on the rope. That's the idea of Newton's third law, is it connects forces acting on different objects in that when one exerts a force on another, the other exerts a force of equal magnitude in the opposite direction on the first object. So by and large, this would show up as like one conceptual question, one no work required type question. So answering something about you're given one force, what is the reaction to that force? What is that equal and opposite force? So we've got several examples of that here. All are pretty good. I think part C is a real good one to look at because it's easy to get confused about which forces are reactions to which other forces. In this example, we had this cantaloupe on a table on the ground. The reaction to Earth's pull on the cantaloupe is the cantaloupe's pull on the Earth, not the force the table exerts on it. And then the reaction to the force the table exerts on the cantaloupe is that normal force that the cantaloupe exerts on the table. So being able to tell which forces are reactions to which other forces could show up as a conceptual question. So that's just another example of that. This is, again, super important. It is how we apply Newton's laws to solve these problems. Your starting point is pretty much always Newton's second law. So there is this thing about Newton's third law first, but that's just that thing about figuring out which way the tension forces act. on something and similar type forces. Second law is how we actually solve for things. If something is accelerating, we use the full second law. If not, that acceleration is zero. Our equation's reduced to this, which is technically the first law. But for us, that is no different than the acceleration being zero in the second law. Okay, yeah, here's that example that I have been talking about as far as tension acting in different directions and accelerations as well acting in different directions. So if you understand why we're choosing the signs we're choosing, and you can reproduce the correct signs for things, sometimes we'll say that one's zero. Sometimes we're saying positive, or down here we're saying negative. If you understand why we did that, and then can do it yourself for other problems like this, like on the practice, there's one where you've got a block on a ramp instead of on a flat surface. If you can set up your equations and get all the negatives and positives right, you're good on anything having to do with systems, because if it shows up, it will be something very similar to this. All right, here is where looking at the incline is important. So there is for sure going to be at least one, probably two questions about something on an incline. Those two questions will probably be about the same setup. It's just questions about different things. So we need to be able to set up our free body diagram for something on an incline, knowing that weight always acts straight down. Just let me go back to green. Weight always acts straight down. Normal force always acts perpendicular to the surface. And then it's whatever other forces you've got going on, tension or friction along the incline. And I wouldn't recommend just hoping that the trig makes sense on the exam. So essentially, I wouldn't recommend, if you're given this theta, trying to like figure out that this is theta, the angle between the weight vector and that axis that the normal force is along. Just say, if the ramp angle is theta, so is this angle between the weight and that normal force axis. Make that one instant. Then the rest is just pretty plug and chug, Newton's second law, find the net force in the x direction, just remembering that now our x direction is along the ramp, and then for the y, that it's perpendicular to the ramp. So elevator stuff I already talked about. There won't be one like this where you're trying to find a reaction force due to these two blocks pushing together or something like that. But the idea is just like with tension, you set it up by drawing the other vector acting the other way with equal magnitude. Friction. The details of friction, as far as its properties, are not the most critical thing. So this stuff up here, not so important. Back to green. As far as the exam goes. What will be helpful is understanding this trend, because static friction is the one that really gets messed up the most. People see static friction and jump straight to this equation, even though that one only applies for the maximum possible static friction. That's when you're told something's on the verge of slipping, or if pulled any harder, it will start sliding, things like that. This is what static friction does in general, is it just resists whatever pull is acting. So if you've got this force acting to the right, the static frictional force is opposing it, is exactly as large. You pull a little bit harder, the frictional force gets larger up into that maximum value. Past that, the surfaces can't kind of maintain that static setup, and so the block starts sliding. When that happens, that max is given by this equation here, and then we enter kinetic friction. Something is sliding. In that case, you can jump straight to this equation. That applies in general to kinetic friction, not just any specific speed or anything, because kinetic friction doesn't depend on speed. You don't need to like memorize the table. It's just kind of helpful to see that this makes sense. When something is wet, there tends to be a lower coefficient of friction than when it's dry, for instance, or when you've got two really smooth things, or sorry, one smooth thing on one kind of rough thing, like, let's see. No, yeah, let's say two smooth things, like ice on ice. That's going to be a lower coefficient of friction than wood on wood, for instance. There is less friction between two sheets of ice than two pieces of wood.
I'm sorry, I have a question.
Yeah.
So you said that the static friction, that was just for the max. Which equation do you use if it's like not the max?
Okay, yep. So there's a question about what we would use if static friction is not at the maximum. That's a good question. If this thing is not moving, then it has to be the case that the horizontal forces are balanced. So if we've only got the one applied force to the right, friction's just opposing that. So we could say that the magnitude of the frictional force is equal to that applied force. If we've got a bunch of forces acting, sorry, I know the kind of cursor thing's going crazy from Zoom, but if we've got like someone's pulling with a rope and then someone's pulling by hand and someone's pulling on the other side some way, what friction is opposing in that case is the net force of all of those. It's trying to oppose the overall other forces that are happening. So in that case, we might say, assuming that these forces on the right add up to something larger than the one on the left, that would tell us, for one, that friction's going to act to the left, but two, that its size is going to be equal in magnitude to F plus T minus that F2. So it just depends on what other forces are going on. Does that answer them? Okay. Yep. Okay. So this other property, not really tested on so much, but just another weird thing about friction, doesn't depend on how large, say, our two blocks of wood are, at least on the large scale, what we can see. It only depends on those tiny little microscopic contact points. So if you have two blocks of wood, you slide one over the other like this versus like this, it's actually the same frictional force in either case, which is weird. There's not going to be anything like this. That's just to give an example of when friction can change directions. These examples are really good ones to look at, both because they have something on an incline in part B, but also they show you how to work with that kinetic frictional force, that what you're always trying to do is saying first it's equal to coefficient of kinetic friction times the normal force, and then you use that in your, or you use what you got from the y direction, what you found out about the normal force's magnitude, in this case that it's equal to the weight. In this case, where something is on an incline, it's equal to that component of the weight in magnitude. You put that back in for your frictional force. So you bring that back into your Fn, and that's going to let you most of the time figure out what you're trying to solve for. Okay, centripetal force. So last exam had some stuff on centripetal acceleration. Centripetal force is the thing that causes that centripetal acceleration. All centripetal force means is a force that acts towards the center of a circular arc. It is not any special type of force. So the takeaways there are, if you're asked what is the magnitude of the centripetal force, you're just asked what is the magnitude of whatever is keeping something moving in a circle. So if a car is going around a curve, it's friction that's keeping it in that turn. And so you're really being asked what is the size of that frictional force. And so your usual equations and things apply. It's just instead you'd set it to something like Fk equals mu k Fn. That equals your mv squared over r, your centripetal force. Okay. This is just another form of Newton's second law. It's just when the acceleration happens to be centripetal. And so if it's gravity, use gravitational force, so on and so forth. Conceptual type questions on this are about directions for the most part. You're told that something is moving in a circle, and you're asked about what direction the velocity points, the acceleration points, or the net force points. So we got something moving in a circle. Its velocity is always tangent to that circular path, as velocity always is to any path. The acceleration is always towards the center of the circle. If it's a uniform circular motion, it's not speeding up or slowing down, as is the net force on the object, which is what we call the centripetal force, a radially inward net force. So directions, getting those right, and magnitude could come up in the sense that even though direction changes, that speed doesn't change, the magnitude of the velocity. The direction of the acceleration is continuously changing because it has to keep pointing towards the center of the circle at all these different points that the object could be at. But the magnitude of that centripetal acceleration does not change. It's always speed squared over distance, over radius. Same for the net force. Its magnitude does not change. So direction for all three changes. Magnitude does not. Okay. So this one with the Ferris wheel, as far as seeing that it's the net force that acts towards the center, and that's what's important. It's a good example for that. In terms of, yeah, really just directions and things is the big takeaway from that one. There won't be something about something going in a crazy vertical loop. It'll be something going along a curve on a road, similar to that Jeep on the first exam. Or you're spinning something in a circle, a horizontal circle. That's all I'm really looking for here. And those are pretty cut and dry. You just say, what is the net force? Could be due to tension, could be due to friction, and set that equal to mv squared over r. Okay, so this one is also a little bit too intense for an exam, but it's additional practice with that thing being on an incline. So that's maybe the takeaway there. Okay, that's chapter 6. So I guess we're about at the midpoint. Questions at this point? Okay. If not, we can keep on moving. So 7 and 8 kind of go together like 5 and 6 go together. We start talking in terms of energy and work instead of forces, although sometimes still remembering forces can be useful. Formula sheet is the same as the one that is on the practice exam. So if you go to the first page of that or second page, I think because it's a little bit longer, it's on there. All right. So kinetic energy and work. To make sense of the equations, that may be the place to kind of look back at this money analogy. Like we said, kinetic is like your checking. It's the most mobile money, most liquid asset. And then potential is like your savings. It's stored up money to be used later, could be transferred to your checking for use. Let's see, external. Well, let's talk about it in terms of things that do positive work and negative work. Something that does positive work is a deposit. It's something adding energy to your system. And then negative work is a withdrawal. So that's things like friction. Whereas this might be like a push from some outside force. Gravity is something that does positive work when something's falling and negative work when it's rising, but that's already accounted for in potential energy. So don't double count gravity when you're solving problems with this. This definition of energy, when we first introduced it, I said it's kind of useless, other than that it's the most correct definition. What's important is energy is just this thing that pretty much we came up with and found out by our models of physics turns out to be conserved, turns out to not change between different parts of the motion of an object or some other change in that system. So it's just sort of a happy accident that things worked out like that. There is a deeper reason for it, but not one that we can get into too much. Energy is measured in joules, as is work. So that's just getting your units right when you're answering something. Kinetic energy for sure shows up. I'm not going to ask you to calculate the kinetic energy of something specifically. It's going to be part of a larger problem. So I won't be like, given the speed, what's the kinetic energy or vice versa. I will say some amount of work is done on something. What is its final speed? If you see something like that, that's work kinetic energy theorem. So I'll come back to that when we get there. The dot product, it's a possibility of not this sort of general look at the dot product. So this whole thing is I don't want to say not showing up. I would say the main things are this version of it and this version. Applying those, it's possible that that could show up in the sense of you're given a force and a displacement, and I want to know the work. You're given those in terms of vector components, maybe. So then you'd use this form, or you're given the magnitude and the angle between them, use that form. Or if you're asked about power, the rate at which work is done, you're given a force and a velocity, and then you do the same thing there. Conceptually, for work, if something speeds up, what can we say about the network done on it? This is a question to Zoom or the room.
Wait, I'm sorry, what did you just say?
If something speeds up, is the work done on it positive, negative, or zero?
Negative.
It's okay. Positive work is a transfer of energy to something, and so it gains kinetic energy. So its speed increases. Negative, you've taken energy away. So our example here, gravity is still a good one. If something is rising up in the air, gravity is doing negative work. It's taking away that kinetic energy, storing it as potential energy, we now realize. But that means that the object slows down. As it falls back down, it's giving that energy back. It's transferring energy to the ball. That's positive work. And so it speeds up. So just knowing when net work is done, net positive work, something speeds up. When it is negative, something slows down. When it is zero, the speed can't change. So we didn't go too much into this, but something moving in a circle, for instance, uniform circular motion, the net work done is zero because it never speeds up or slows down. Its direction changes, but it doesn't change speed. So the net work done is zero. And that's because the force is always perpendicular to the displacement in that case. Okay, calculation-wise, that's an important one. And this is what I meant by potentially using that dot product. It's not as much of a critical thing for me on this one. This is all just deriving work energy. What we need is this, the result of it. It says that net work done determines the change in kinetic energy, which is what we just set up here. So if the net work done is positive, the change in kinetic energy is positive, the final kinetic energy is larger than the initial, so speeds up. Network is negative, final is less than initial, slows down. Network is 0, no change in kinetic energy, no change in speed. This is just the mathematical statement of those ideas we just went through. So I would say exam problem on this, on work energy theorem, sits somewhere between these two, in that you're given some information about the speed and how it changed maybe, and I want to know the net work done. So you would, for that, say it's 1/2 m times the final speed squared, minus 1/2 m times the initial speed squared, because that's our change in kinetic energy. That gives us the net work done, or go the other direction. Once you know the net work done by a force, tell me how it changes the speed of it by using that change in kinetic energy. So this one shows finding net work done and applying it to that change in kinetic energy. So I think it's a really good example in that way. There just probably won't be one that has all these different forces acting in all these different directions. It would be a simpler setup, but a very similar idea. Also, just things like this that you can quickly throw out the work done by gravity and the normal force if something's sliding along a surface, because both are 0 in that case. Work done by the gravitational force. I'm not so worried about lifting and lowering things, just that this is an application of that idea that positive work increases kinetic energy, negative work decreases it. So if you realize that something is slowing down, which it would be when something is being thrown upward in the air, then negative work is being done. If something is speeding up, like when that object's falling back down, positive work is being done. So that's more a conceptual thing. How we actually use these ideas is when we talk in terms of potential energy. And that's when we stop looking at the work done by gravity, look at negative that work, because that's a change in potential energy. So for things where you've got something moving up and down, probably want to think in terms of gravitational potential energy rather than the work done by gravity. This is still just another example of work kinetic energy theorem. And so it's good to just see how we can solve for different things. But again, if you've got the gravitational force doing work on something, it's better to look at it in terms of potential energy. Similar for a spring. So we went through all this to get to the idea that the work done by a spring is given by that. But there can be conceptual questions like, let's see. So when you stretch a spring and let it go, it's going to tend to try and pull that object, the block in this example, back towards equilibrium. And in doing so, it's going to speed it up. It's going to do positive work on it. As the block compresses, it's going to slow down that compressed spring is going to slow the block down. So the spring's doing negative work once the block has overshot that equilibrium position. So once it's like over here compressing the spring. But then when it comes to a stop and goes back the other way, that compressed spring is now speeding it up. And so doing positive work. And then once it overshoots again, the stretched spring is slowing it down and doing negative. So the best way to state how we account for the work done by a spring is positive if it is moving back toward equilibrium, toward that relaxed state. Negative if moving away from it. And I sure wish I had said that the first time. That probably would have made it much less confusing than I think I made it. But that is the idea, is that it's always trying to bring the block back towards that equilibrium position, and it does so by doing work to bring it back. Similar to how when you throw a ball in the air, gravity is trying to pull it back down to the earth. So when it's doing that, when the ball is moving back towards earth, positive work is being done. When it's moving away from earth, negative work is being done. Okay. But otherwise, if you're asked to find the work done by a spring, it really just is direct application of this formula. More likely, it will be, again, better to use elastic potential energy, this energy resulting from the work done. There could be a question on the work done by a variable force. I think at this point there is. It will not be about integrating in the strict like calculus sense. It will be like problems we've already seen where we've got something very blocky so that you can break it up into, hey, that's a rectangle. I know the area of that. That's a little triangle. That's another rectangle, another rectangle. Integrating in that sense, finding the area under the curve just with some geometry, length times width, 1/2 base times height for a triangle. Adding all that up to figure out the total work done between 2 points. But it is, I think, relevant to realize, like, say our 2 points are from there to there. Maybe that's 5 meters and 15 meters or something. The work done from 5 meters to 15 meters is the work under this, or sorry, the area under this curve between those two endpoints. That's all you need to find. And then that could lead into like, tell me if you're given a certain speed at one endpoint, what is the speed at the other? That's when work energy theorem comes in. Okay, power. I'll just say power's not going to be on there. The work stuff is more important as far as the exam goes. No power stuff. Oh, although that is an example of using the work done by a spring, calculating it. So maybe just part A of that. So that's not there. Chapter 8, potential energy. So this is, like I said, the actual calculation useful bit. So knowing that it is doing the opposite of whatever the work is. So if the work done is negative, potential energy is increasing. If it's positive, potential energy is decreasing. And that led us to that formula, work equals negative the change in potential energy. The same idea applies here, and the same things stated about moving away from or towards that relaxed state. So if it's moving back towards it, the work done is positive, and so the potential energy in the spring is decreasing. It's relaxing. Whether that means coming back from being stretched or being compressed, that doesn't matter as much as it's just relaxing. If it is moving away from that equilibrium point, work done is negative, the potential energy is increasing. So conceptually, that's why this is relevant. For problem solving, let's see. For problem solving, you need to remember that this is the elastic potential energy. That's just the formula for it, where X is how far the spring is stretched or compressed from that relaxed state. And then gravitational, that formula. And from here, I think I'm going to jump straight to conservation. So conservative versus non-conservative forces, don't worry about. It's just that that leads us to, if we only have conservative forces acting, then we can say energy is conserved. So the only way in which you need to think about conservative or non-conservatives is if you have things like friction acting and it's doing work, you can't use this conservation of energy formula down here. You have to use the work done by non-conservative forces determines the change in mechanical energy. Although we're gonna use the form way down here of that, this one, use that form for any problems involving friction. Okay, so to get to that, don't worry about this for the exam. This is just deriving the work energy theorem in this different form and then seeing how that reduces to conservation of energy. So I don't know, it may help to see that conservation comes about by saying that non-conservative forces aren't doing work, but at the end of the day, this is what you're applying to problems, as long as friction's not acting. Okay, so these examples are good conceptually about things like where is the kinetic and potential energy the maximum. So kinetic's maximum when it's moving fastest at the bottom of the swing, potential's maximum at that maximum height. Similar here, but that's conceptual type stuff. Calculation, this one's a really good example. There's several in the practice exam like that. Potential energy curves, I anticipate one question at most. And it's just going to be like one very direct question of like, which point is the neutral equilibrium? Which one's stable? That sort of thing. Or where's the turning point? It's not going to be a whole lot of calculation type stuff for this. So in this particular example, it's not so important telling me the speed, for instance, of this thing. For me, a ranking type problem would be more relevant for the forces, or when can it clear a gap or not, and when is kinetic energy largest, which is when you have the biggest difference between your mechanical energy cap on things and then your the bottoming out of the curve. So this point is lower than any other. That's going to be the lowest potential energy and so the highest kinetic energy. Okay, and then this is the work done by non-conservative forces type formula, where we said that this is like what's in your account to start with. This is any deposits, this is any withdrawals, this is what you're left over with in your account. And you can use that balancing of things to account for where the energy went and how fast something's moving or how high up it is when it comes to a stop, that sort of thing. Okay, this is not on there. This example is real good, and those extra ones that I posted. There could feasibly be something like this on the exam for dealing with when friction is present. Might be simpler as far as it looks, but the math works out practically the same, which is the nice thing about energy conservation and work done by conservative, non-conservative forces, that stuff. Okay, so that is the end of reviewing the notes. Questions on the practice exam? Yeah. I think it's just you and me in here, Adam. So if you have any questions, let me know. If not, maybe I'll just look at a couple here. Let's see what we have. Okay. All right. Well, I'll just pick out a couple and do them for anyone who needs a few more practice problems to look at. So I think this is a good one. We've got a force of 15 newtons acting at this angle of 25 degrees on this block of mass 6 kilograms. The floor is frictionless. We don't need to worry about a frictional force. It's applied by this cord. All that matters for is that the force is acting along the rope, along the cord. Okay, so what is the magnitude of the normal force on the block? So let's start drawing in any forces that are acting. Definitely got gravitational force. Definitely got normal force. It is perpendicular to the surface. And that's it, in addition to this one applied by the cord itself. So our free body diagram, we just make a dot for the object, draw in all our forces, leaving that dot, pointing away from it. Okay. Note any angles going on because we then need to break things into components. Notice I really am not even looking at what it's asked me to solve for at this point. I'm just going through the motions of this. So I have to define my axes, just pick the most convenient ones. In this case, it's those because 2 of the 3 forces fall along them. So I just need to break this one applied by the cord into components, vertical and horizontal. Those are the components that add together as vectors to give our overall one. And so instead of looking at that force, we're just now looking at these 2 components. All right, now I am finding my net force in the X direction, net force in the Y direction. In the X direction, I just have that horizontal component of the force applied by the cord. That's going to be F cosine theta because that horizontal component is adjacent to that angle theta. It's touching the angle. We can rotate our force F into that angle and or through that angle to get to our horizontal component. And it's to the right, so that's why it's positive. That ends up being the only horizontal force. So that is equal to the mass of the block times its horizontal acceleration. In the Y direction, we have normal force acting upward. We also have gravitational force acting downward as usual, but we also have that vertical component of this force applied by the cord. So that is F sine theta, and from our picture, we see it's acting upward. That's equal to the mass of the block times its vertical acceleration. If it's pulled along a floor, it is not accelerating vertically. So that side is 0. That tells us rearranging, our normal force is equal to gravitational minus F sine theta. Magnitude of gravitational force is mass times gravitational acceleration. So 6 times 9.8 minus 15 sine 25 degrees. That's going to be our normal force. But I didn't really care that that's what I was asked for up until I had set up all my net force equations, draw my free body diagram, all those things. 6 times 9.8 minus 15 sine of 25 should be 52.5. Yeah, 52.5 newtons. 53 if we're rounding. And if I go over to filled inversion, does that look right? Yeah, 52.5. All right, so notice it is lower in value than the weight in this case because that applied force component is acting upward. That's tending to lift the block off the ground a little bit. It's not pressing as hard on the ground's not pressing as hard on it. What is the magnitude of the block's acceleration? Well, we said it's only accelerating horizontally. The vertical acceleration is 0. So I already did most of the problem. I've got that acceleration is F cosine theta for m. It's 15 cosine 25 over the 6 kilograms, and that is 2.3 meters per second squared. Is that, yep, 2.3. Okay, let's see. All right, I'm gonna do this one, and I'll do this one. Let's see if there's any others. I'll do. I'll do that one. All right, I'll do those for chapter 6. So this one's pretty quick. 40 Newton crate, that's its weight is 40 Newtons. That's what it's telling us, gravitational force. A 12 Newton horizontal force is then applied to it. Whether we draw that as a push or a pull doesn't matter. I draw it as a pull because that's going to look more like our free body diagram that we draw in a second. Coefficients of friction are static is 0.5, kinetic is 0.4. It's lower, like we'd expect. What is the magnitude of the frictional force on the block? The reason it's telling us both these coefficients is because it really depends on if we're getting the block moving with this force or not. And that depends on if, since it's starting from rest, if the static frictional force is going to be enough to keep it from moving, if it can become up to 12 newtons. Because if this pull weren't here, static frictional force would be 0. If this pull were 6 newtons and static frictional force could pull back that hard, it would be 6 newtons. But in this case, we're just saying, is this smaller than my maximum possible static frictional force? Because if it is, the static frictional force will just be 12 newtons. If it isn't, then the block's going to start moving, and we're dealing with kinetic friction. So how I test that is, what is my maximum possible static friction? That's what's the coefficient of friction times the normal force. Normal force is acting upward. This pretty much is my free body diagram, so I won't draw it over. These are my axes. My net force along the x direction is 12 newtons minus whichever type of frictional force we have here. I don't know if it's going to be equal or not. I don't know if it's static or kinetic because I don't know if the 12 newtons is going to be able to get the block moving or not yet. So that's going to be 12 newtons minus F, and that's going to equal mass times the acceleration. If they're balanced, acceleration is 0. If they're not, the block does accelerate. In the y direction, normal force minus gravitational, which is 40 newtons. So normal force is 40 newtons. That's what we need up here. It's 0.5 times 40 newtons is 20. The maximum possible value that this static frictional force could be is 20 newtons. That's definitely enough to counteract a 12 Newton pull. And so our answer is not 20 newtons. That's the maximum value. Our answer is, what is the actual value of static friction here? And that's just what it needs to be to oppose this pull. Answer is 12 newtons. To give you a sense of, say it was moving, well, how would we do this? Let's say this pull was instead 30 newtons. In that case, the magnitude of the frictional force, well, we found out this pull is greater than the maximum static friction. So the crate's going to start moving. Then we're dealing with kinetic friction. In that case, it is always this formula. And so that is going to be 0.4 times 40, which is 16 newtons. That would be our frictional force in that case. Okay, so kinetic's actually the easier one in a lot of cases to apply. Static's a little tricky. Okay, what is the acceleration of block B when block A is released? So I've got block A, mass 10 kilograms on a 30-degree incline. Call this mass of A. Coefficient of kinetic friction is 0.2. The attached string is parallel to the incline and passes over a massless frictionless pulley at the top. Massless frictionless just tells us don't worry about the motion of the pulley itself in this problem. So that string is going to apply a tension force on this and this, and it is opposite the way that the block itself pulls on the string. This is the force the string exerts on either block. Block B is a mass in B, and we want to know the acceleration of block B. I'm just going to call that A because since these blocks are attached, assuming the string stays taut, it doesn't go slack, that acceleration has to be the same for both blocks. When block A is released. So once block A is released, there's nothing holding it down. It's just going to move as it would based on the forces acting on it. So we've got gravitational force, maybe call that FGA. We've got the normal force from the ramp. We've got the kinetic frictional force. Now, I don't know which way this force is going to act. So I have to make a choice. I say, I think block A is going to, no, you know what, I'll go the other way. I think block A, because of its weight. It's going to have a weight once we calculate it that is significantly larger than the weight of block B. Even though it's on an incline, unless if that acts down the ramp than the full weight of the block, I'm going to guess that I think it's going to slide down. So I'll say that's the direction the block's going to slide. And so accelerate, speed up from rest. And that means to oppose that motion, the frictional force must be up the ramp. Okay. And then on block B, my only other force is gravitational. So let's turn that into free body diagrams. For A, actually I'm going to draw them up here, save some room. FGA, tension, kinetic friction, normal force. And then block B, gravitational force and tension. And need to choose some axes. They don't have to be the same for both. I'm going to choose these for block A because 3 of my 4 forces lie along them. Choose this for B. And I need to resolve any forces that are not along those axes into components. It's just the gravitational force on A that's not. And like I said, at this point, try and commit to memory. That angle between the weight vector and that axis is going to be theta. So in this case, 30 degrees, which I guess I forgot to label that as theta. Okay, so I need to break my gravitational force into components. And that's going to be FGA cosine theta. It's the side adjacent to that angle, and then FGA sine theta. Now I set up my second law for both. So we'll start with A. We've got tension minus FGA sine theta plus kinetic friction equals the mass of block A times its acceleration, which really, since I guessed that acceleration points down the ramp, should go that way. It should be negative. And then in the Y, normal force minus FGA cosine theta. So mass of block A is capital A, times the vertical, meaning away or towards the block acceleration, sorry, away or towards the ramp acceleration, but that's 0. It's not leaving the ramp, it's sliding along it. So this whole thing goes 0. So the normal force is equal to FGA cosine theta. So I'm going to bank that for this next bit, which is, let's just jump to block B. Net force on it is pretty easy. It's just in the Y direction. And if I call up my positive direction, that's tension minus FGB, and that equals mass times. So if block A is sliding down the ramp, that would mean block B is going up at that same acceleration. So I would call that one a positive A. And so I want to find that. I then need to eliminate tension because I don't know it, although it's asked for in the next bit. I want to find acceleration. So how can I get rid of tension? Well, I've got the tension I'm going to put everything else on this other side equals FGA sine theta minus FK minus mass of A times that acceleration, because that was negative. And since that's the same as this tension in magnitude, even though those forces act in different directions, I can substitute that in right here. And so at FGA sine theta minus FGB minus kinetic friction, which I'll just go ahead and say is kinetic times normal force. And we found that normal force on the block to be FGA cosine theta minus mass of block A times its acceleration. And then this was equal to mass of block B times its acceleration. Looks like a nightmare, but the only thing we don't know in this is the acceleration. We know the masses of our two blocks, so we can find their weights. We know that angle of the ramp. We know the coefficient of kinetic friction. A is the only unknown. So if I isolate for it, all I have to do to do that is bring this term over to the right side and divide by MA plus MB. So if I do that, that's equal to FGA sine theta minus FGB, FGA cosine theta over MA plus MB. And then just remember that FGA is the weight of block A, FGB is the weight of block B. And if I put all that in, I'm gonna get, if I'm very careful about it, let's see, what do we have? A is 10, it's 9.8 times sine of 30 minus 3 times 9.8, that's weight of block B, minus coefficient of kinetic friction is 0.2 times 10 times 9.8 times cosine of 30 over the mass of both added together is 13. I get that my acceleration 0.2 meters per second squared. And so I got a positive number. That means that my acceleration should be actually up the incline, right? My acceleration was actually positive, and so should point along the, oh, no, I'm sorry. That is the correct magnitude. So we already accounted for the direction and we got the direction right. If we had gotten a negative here, then we would have said, oh, I got the direction wrong because I thought I had already accounted for any negatives that could show up. So the acceleration is actually down the ramp like this. My mistake on that. So let's check that. .69. All right, so let's double check my work here. It is down the ramp, so that's encouraging. Let's see, we got tension, gravity, kinetic friction up the ramp. And that. Then I've got normal force, cosine theta. Okay, and then tension, G equals mass times that acceleration. And if I put that all together, I should get FGA cosine theta. Okay, and I'm not seeing any issues with the setup. So let me check my numbers here. Total mass is 10, 3 is 13. I am not sure where it went wrong. Let's see, when I substituted, that's FGA sine theta minus FK minus that. Yeah, I don't see a problem here. So I'm going to go back in after this and check on the number I put there if I copied over that answer right. And if it is, I'll take another look at my approach, but I don't see anything wrong with it. So I'll have to come back to that. Okay. So take that as a grain of salt. I think it's 0.2. The answer given is a different number. So I'll take a second look a little bit later. I don't want to bog down the pacing. So I think I'll just do this one extra example because the extra questions on Wiley that I posted for these next two chapters, I think are pretty representative of some good practice problems. And if you have questions on these other two chapters or just anything, I don't know why that's there. Just email me. I'm happy to take a look at them in that case, but I want it to be as directed as it can be. I don't want to waste too much time on problems that people are comfortable with. Let's just see what the right answer is on this. Centripetal force is mass times speed squared over radius if the radius is doubled, keeping the speed the same. So that doesn't change. This just goes up by 2. That brings the whole thing down by that factor of 2, right? Because we went to 2r. So it should be, I'm guessing somehow that one got blocked out, but it's that one. 1/2 is great. Okay, so I'll just do this one and then cut it off there, and I'll take a second look at that problem that I'm not getting the same answer as is given. Okay, one end of a 1 meter long string is fixed. The other end is attached to a 2 kilogram stone. The stone swings in a vertical circle, passing, actually, I'm going to jump to this one. So that's a vertical circle. That's a little bit more complicated because what happens is down here, you're going to have gravitational force and tension acting opposite each other. Here you're going to have tension, gravitational force acting together, and that changes the size of the tension force in this case, and it's a little bit trickier. Although we could just say it's tension minus gravitational is our net centripetal force. And so tension is G plus mv squared over R. So 2 kilograms, I'll just factor out mass, times 9.8 plus 4 meters per second. Square that over 1 meter. So that's 16 plus 8 times 2, 52. Just since I said I'd do it. And let's hope that one's right. Okay, so yeah, that was half as great. And then 52. All right, and then just let's check if we get 30 for this one. 0.2 kilogram stone is attached to a string and swung in a circle on a horizontal surface. So it's on a surface, swinging around in a circle. That's 0.6 meters. It has a certain mass, 0.2 kilograms, and it's making 150 revolutions per minute. Why that might be relevant to us is if we think back to, I think that was chapter 4, whenever we talked about centripetal acceleration, we also talked about the fact that the speed in the uniform circular motion is circumference over the period of the motion. And so we're not given the speed here. This might help us find it, but it's going to require us to find this period of the motion. That's the time it takes for one revolution. And so if it's taking 1 minute for 150 revolutions, it must be that for 1/150th of that, so 60 seconds, for 150 revolutions, it must take 1/150th of that for just one revolution. And so 60 over 150, 0.4 seconds is our period. And so our speed is 2 pi times 0.6 meters over 0.4 seconds. I get 9.4 meters per second. And that's going to be relevant in that our centripetal force is the force provided by tension here. That's what's acting towards the center of the circle. So tension, that's mass times acceleration. Centripetal is v squared over r. So our tension is mass is 0.2 kilograms times speed 9.4 meters per second squared over radius of 0.6 meters. We're expecting 30 out of this. Let's see. Yeah, 29.5 round up to 2 sig figs, it looks like. That's 30 newtons, or 1 sig fig, I guess. All right, so that is, I think where I'll stop. If there are questions on additional practice problems, maybe down in chapters 7 and 8, let me know. I just think chapters 5 and 6 are the most kind of technical as far as applying everything, so I wanted to emphasize those a little bit more. I'll take another look at this one to make sure I didn't make some small mistake somewhere that messed up the answer, or maybe I made a big mistake and I need to go back and take a closer look at that. So I'll email about that once I have figured out what it is that I did here. I'm hoping it's right, but if not, I'll post a corrected version. Okay, that is it, unless there's any last minute questions from, I guess, just Adam. All right, well, I guess there are not any questions, so I'll stop the recording. But I'll see you all tomorrow. Again, email if you have any questions. Anytime tonight, if I'm up, I'll answer. So don't worry about what time it is when you come to a question. All right.